Thank you. Okay, today is the 28th, I believe, and we are talking about sequences and series. This definitely has ideas you've seen. I'm not sure if you've seen these words before, so let me know if you have. A sequence, at its most basic, a sequence is just a list of numbers. So in this case, the math makes sense with the English, because you should know that that sequence, when things are sequential, they're listed in order, right? Now the list of numbers we're particularly interested in follow patterns. And recognizing those patterns is going to be interesting. I'm curious which ones of you will see these patterns quickly and who won't. A series is a sum of the numbers in a sequence. Super simple example. Let me see what your book's notation is, just to make sure. I don't really get, okay, all right. Example of a sequence. 1, 2, 3, 4, 5, 6. Tell me something about this sequence of numbers.
They increase
by 1.
Increase by 1, start by 1. You could also call this the set of counting numbers. There's a whole bunch. This is the simplest, earliest sequence in all of human history. So that's your basic sequence. A series is a little different. Series would be the series of the, how am I going to say this? Yeah, when you're looking at a series, you're talking about the sum of some number of terms in this.
So what we have.
Well, some books would say, like, for an example, S sub 4 would be one way to kind of say what is the sum of the first 4 terms of this sequence. And what would that be? 10. So S sub 4 would equal 10 in this case. Do you think the patterns stay this simple for long? No. Not in this course. Have you guys heard the term sequences and series before?
It's like on
Yeah, I've
the
heard series used in this.
Okay, but sequence you had? Okay, and it's on the ACT now? All right. Okay. Because I want to get a little bit covered here. I'm not going to go into the derivation of this right now. Just some quick notations. A sub n is the most common way to refer to the nth term in a sequence. Now, if you get the pattern of the sequence, finding a sub n isn't necessarily that hard. For example, if I have a sequence that's 2, 4, 6, 8, 10, 12, ... What's the pattern here?
Plus 2.
Plus 2. Okay. Tell me the pattern in terms of where we are in the sequence. For example, if I say a sub 1 is 2, a sub 2 is 4, the subscript here refers to the first term in the sequence.
A sub 2n.
So a sub n would equal what?
2n.
Would equal 2n, yeah.
2n. This is called, it's either explicit or implicit, and I'm suddenly drawing a blank. Does your book use this term in this chapter? Because if not, I'll be doing it. Okay, I'm going to call this an explicit rule, because you know what? That works in English, even if it doesn't work in math. This basically, now I'm really thinking it's the implicit rule. Oh well. At any rate, it's a rule that tells you how to find the nth term just by knowing what position it holds in the sequence. So, following this rule, what would a sub 5 be?
10.
What would a sub 52 be?
104.
104. Okay, so using your, whatever it's called, rule, your something implicit rule, a sub 5, you can quickly determine what the nth term in any sequence will be. That's if you can see the pattern. Some patterns are easier to see than others. We'll talk about two in general today.
Is there a way of figuring out a pattern?
One single way that works for everything? No. Are there ways to figure out patterns based on sort of families of patterns and what types of things? Yeah, there's a lot of tricks, and there's a lot of different ways. And what you have to get, where you need to get some skill is recognizing what type of sequence you're looking at. Yes, sir?
Does a sequence have to follow a rule by definition, or can it be arbitrary?
I'm honestly not sure how general the word sequence is used in math. I mean, the short answer to your question is you can make a list of numbers in any pattern you want. Though there's a lot of psychological studies that show it's surprisingly hard, if not impossible, to come up with a random.
Real.
Yeah, real random is very hard to achieve. You've heard that before, right? Whether it's I'm actually not sure if the formal definition of sequence means you can fit it to a pattern or not. But if sequence just by my definition of list of numbers, it doesn't have to follow a pattern. There are patternless lists of numbers. In fact, there still is not a formal proof that there's a pattern to prime numbers. So if you start listing the prime numbers in a sequence, there is no a sub n rule for the nth prime number. There is a theorem, there's a function that they think helps you predict them, but that's actually one of the outstanding mathematical proofs that hasn't been finished yet. No one said it works for all infinity. So there's an example of what you just asked, prime numbers. Now, let's see. One other rule. Actually, come back over here a second. This one I know I'm getting the name right. There is something called a recursive rule to a sequence. A recursive rule doesn't help you find the nth term based on some formula involving n. A recursive rule tells you what the nth term is doing by describing its relationship to the prior term. Okay, so what's happening in between these terms here? 2 is being added. Okay, so for any term here, I could say that the nth term is equal to the prior term plus 2. Now, because you don't know if you started on an even number, an odd number, a decimal, an irrational number, this doesn't, you can't just look at, I can't just throw you this and say, hey, what's the 50th term? If this is all you knew, if you didn't have this list to look back on. If I threw you this and said, what's the 50th term, the only honest answer you could give me is, I don't know, but it's 2 more than the 49th term.
Wait, what about like would you be able to find a sub 1?
Normally to use a recursive rule, you have to be given a sub 1 and the recursive rule to be able to do anything. And then it's fairly simple. Start at a sub 1, follow the recursive rule until you get what you want to. But recursive rules don't have to be simply addition. They can be multiplication, they can be all sorts of crazy things.
Can't you just do like, if they give you a is 52, wouldn't that just be a 52 plus a?
Good question. I'm glad you asked that actually. When n is a subscript, all it describes is the position that the number holds in the list.
Not the number, so n is
Right.
like different numbers.
And the best answer for Joey's question is, sometimes it's either unclear or impossible to come up with a simple relationship between the position in the list and the value of the number holding that position. In this case, I set up a sequence where, however far you went, the first, third, second, third, fourth, fifth position, the number in that position would be twice that place. But that does not have to be the case at all. In fact, there's a very common example that you might have heard of, the most famous number sequence that is easy to do as a recursive rule and very, very hard to describe in a implicit rule is the Fibonacci sequence. I think I'm spelling that right. You guys ever heard of this one?
Yeah.
Not me.
You get a term by
You add the previous 2 terms.
2 terms, yes, to get the next term
Yeah.
in the sequence, right?
And you start with 1 usually, right?
Yeah, start with 1.
What is that?
You do 1 twice.
Yeah.
It actually has a very specific origin that helps you remember the beginning of the Fibonacci sequence. And it turns out to have implications in biology because the question that, I think it was Leonardo of Pisa was his name, Fibonacci was his Latin name, Leonardo was in his name somewhere. The question this guy asked was, had to do with, imagine rabbits breeding very consistently in the absence of predators. And he came up with a consistent pattern. I don't think it accurately describes all rabbits' procreation, but he did ask himself a question. What if you had a single breeding pair of rabbits? So each number in the sequence started out representing a pair. These rabbits can mate once a month, and they grow to maturity in a month. Okay? So boom, you've got this pair of newborn, I should say that, rabbits sitting here. Okay, they're newborns, so they're not mature yet.
Wait, so a single pair of rabbits always has two?
There's two rabbits in this one number here. Okay? So they're born, they're there, they just sit there. They do what baby rabbits do. I don't know, punch each other and fight over toys, I guess. But they're not sexually mature yet. So 30 days later, they're still sitting there. And suddenly they're mature. And then they do what rabbits do and they notice each other. Okay? They are still there 1 month later, and so are their new baby rabbit pair, which conveniently is also a boy and a girl just born. Start them in a different color, actually. So now we've got two pairs of rabbits. Mom and dad, and their offspring. A month later, mom and dad, immediately after having their offspring, get back to what rabbits do, so that a month later, mom and dad are still there, and mom and dad have had another pair. Meanwhile, these guys who were just born don't do anything for a month, and then they're still just there. Mom and dad do what they're going to do. A month later, they're still there. And, I have a black marker? Got, I think, a teal one over here. Yeah, oh yeah, got that one there. And then, hey Jen, they have another pair. This pair is now a month old. Yeah, we can. And this pair is still there, plus